Welcome to Introduction to Data Acquisition and Signal Conditioning.
The previous webcast in this series covered amplification, instrumentation amplifiers, and filtering. The agenda for today's presentation covers Part 2 of Fundamental Signal Conditioning. This includes 4 topics: attenuation, isolation, linearization, and circuit protection. We now come to the topic of attenuation and voltage dividers. Most data acquisition system inputs can measure voltages only within a range of 5 to 10 volts. Any voltages higher than this have to be attenuated. Simple resistive dividers can easily attenuate any range of voltages, but 2 drawbacks complicate this simple solution. First, voltage dividers present substantially lower impedances to the source than direct analog inputs. Second, their output impedance is much too high for multiplexer inputs. For example, consider a 10-to-1 divider reading 50 volts. If a 900 k-ohm and a 100 k-ohm resistor are chosen to provide a 1 megohm load to the source, the impedance seen by the analog output is about 90,000 ohms, still too high for the multiplex reading to be accurate. When the values are both downsized by a factor of 100, so the output impedance is less than 1,000 ohms, the input impedance seen by the measured source is 10,000 ohms or 2,000 ohms per volt, which most instruments cannot tolerate in a voltage measurement. So simple attenuation is not practical with multiplexed inputs. The low impedance loading effect of simple voltage dividers can be overcome using unity gain buffer amplifiers on divider outputs. A dedicated unity gain buffer has a high input impedance in the megohm range and does not load down the source, as does the network in the previous example. Moreover, the buffer's output impedance is extremely low, which is necessary for the multiplexed analog input. Not all voltage divider networks connect to a ground or a common reference point at one end. Sometimes a balanced differential divider is a better solution for driving the data acquisition system's input terminals. In this case, the common mode rejection ratio, CMRR, of the differential amplifier effectively reduces the common mode noise that can develop between the different grounds in the system. Here we see a typical high voltage input card for a data acquisition system, which contains a balanced differential input and jumpers for selecting an input voltage range of 10 volts, 50 volts, or 100 volts. The input circuit also compensates for long lead wire capacitance that tends to form on AC voltage divider. This AC divider would reduce the accuracy of the measurement. Some data acquisition systems employ special input modules containing high voltage dividers that can easily measure up to 1200 volts. They are insulated to handle the high voltage and have resistor networks to select a number of different divider ratios. They also contain internal trim potentiometers to calibrate the setup to extremely close tolerances. Voltage divider ratios applied to DC voltages are consistently accurate over relatively long distances between the divider network and the data acquisition system input when the measurement technique eliminates the DC resistance of the wiring and cables. These techniques include a second set of input measuring leads separate from those that apply power to the divider, such as the Kelvin connection. Voltage dividers used on AC voltages, however, must always compensate for the effective capacitance between the conductors and ground or common, even when the frequency is as low as 60 Hz. It's not uncommon to find that when the AC voltages are calibrated to within 0.01% at the divider network, the voltages reaching the data acquisition system input terminals may be out of tolerance by as much as 5%. This is because the lead capacitance enters into the divider equation. One way around the problem is to shunt the data acquisition input terminals, or the divider network, with a compensating capacitor. For example, oscilloscope probes contain a variable capacitor precisely for this purpose. The probe capacitor is adjusted to match the oscilloscope's input impedance and, as a result, faithfully pass the leading edge of the oscilloscope's built-in 1000 Hz square wave generator without undershoot or overshoot.
To view the remainder of this tutorial, please visit the on-demand tutorials in the resources section on Measurement Computing's website at www.mmc.com. mccdec.com.